Okay, so now let's start with studying what are the allowable states of a 2-qubit system. So as before, what we are going to do is consider 2 atomic qubits, which means that, let's say we have 2 hydrogen atoms, and we are thinking of the states of the electron. In fact, 2 particular states, the ground state and an excited state, which we use to encode for 0 and 1. And so now, since we have 2 such atoms, the 2 electrons can be used to represent classically 2 bits of information. So the possible states are 0, 0, 0, 1, 1, 0, and 1, 1. What about quantumly? Well, the superposition axiom tells us that the state is in general a superposition over all these 4 possibilities, that the system doesn't make up its mind which of these 4 states it's in. And so you have a complex amplitude for each of these 4 possible classical states. Say, for example, alpha 0, 0 is the complex amplitude of 0, 0. And as before, we have this normalization condition. The sum of the squares of the magnitudes of these amplitudes adds up to 1. The normalization condition is important because it tells us what happens during a measurement. So if you actually look and see what the state of the system is, you'll see each of these 4 possibilities with probability the square of the magnitude of that corresponding amplitude. Moreover, if you happen to observe 0, 0, then the new state of the system will exactly be 0, 0. So let's do an example. So suppose, for example, that the state of the system was 1 over square root 2, 0, 0, plus I over 2, 0, 1, minus 1 over 2, 1, 1. So you can check that this is a valid state of the system because it satisfies this normalization condition. So now what happens when you measure the system? Well, what happens is that you see 0, 0, that both of the electrons are in the ground state with probability. So the probability that you see 0, 0 is 1 over 2, the square of this. And then the new state is 0, 0. The probability that you see 0, 1 is a quarter, and then the new state is 0, 1, etc. Okay, but now you could ask a different question. What happens if instead you measure only the first qubit? What's the result of that measurement? Okay, so let's try to understand that. So again, we start with some quantum state of the 2 qubits, and let's say we have our same example that psi happens to be 1 over square root 2, 0, 0, plus I over 2, 0, 1, minus 1 over 2, 1, 1. So what happens if you measure just the first qubit? What's the probability you see 0? So the answer is the probability that you see 0 for the first qubit is exactly the same as the probability that you would see a 0 if you measured both qubits. Okay, so if you measured both qubits, what's the probability you would see a 0 on the first qubit? Well, you would only see a 0 if you had this outcome or this outcome. Well, this happens with probability alpha 0, 0 squared, and this happens with probability alpha 0, 1 squared. And so that's the chance you see a 0. So in this example, it would be 1/2 plus a quarter, which is 3/4. Now, what's the new state if you happen to see a 0? Well, the answer is really quite elegant. What you do is, if you happen to see a 0, then what you end up doing is discarding all the parts of the superposition which are incompatible with the answer. So you discard these parts of the superposition. And so what you're left with is this superposition, but it's not normalized. So you just normalize it. So the new state will be alpha 0, 0 plus alpha 0, 1, 0, 1 divided by square root of alpha 0, 0 squared plus alpha 0, 1 squared. So now what you should do is check that the amplitudes, well, the amplitude for 0 is what? Well, the amplitude for 0 is this fraction. What you should do is check that the square of the magnitude of this plus the square of the magnitude of the amplitude for 0, 1, they add up to 1. Okay? And this is something that's easy to check. So going back to our example, what's the new state if you happen to see a 0 for the first qubit, when you measure only the first qubit? Well, we'd cross off this, and then we'd renormalize. So we'd get 1 over square root 2, 0, 0, plus I over 2, 0, 1, and then you'd have to divide this by the square root of this squared magnitude plus this squared magnitude. Right? What's the magnitude of this squared plus this squared? It's 3/4. Okay, so that's the answer, which you can further simplify, but we are more concerned here with the actual logic of the situation.